Welcome to the workshop. We want to take another look at an example. Here we're going to use the ratio test to determine the convergence or divergence of a series. The series that we're looking at is the sum from 1 to infinity of 3 to the n divided by n squared times 2 to the n minus 1. Now, what we see here are a couple of different things going on. If we were to kind of ignore the numerator and denominator, right, just see 1 over n squared, this would actually be a p-series that converges. But we're taking each of those terms and multiplying it by something that has kind of a geometric series look to it. So I'm not multiplying the two series, just the individual terms together here. But that geometric series with a ratio of 3 over 2 essentially would diverge. So we have convergence terms, right? Something that looks like it could converge multiplied by something that diverges. So as 1 over n squared goes to 0 and 3 to the n divided by 2 to the n minus 1, right? That's going to go to infinity. As these two things work against one another, what happens? Is it overall going to end up just, maybe it still goes to 0, but it goes to 0 too slowly, like 1 over n, and it still diverges. Or maybe n squared works quickly enough that it is able to make it small, and so it goes to 0 quickly, and then we're able to get a sum for the series. So it's just an investigation into how the numerator grows in comparison to how the denominator grows, essentially, is what we have going on there. So how does this work out? Well, if we want to implement the ratio test, again, our ratio test here is very useful when we have essentially, ratios themselves is typical, but we have something that looks like it could converge multiplied by something that looks like it could diverge. The ratio test tends to be pretty helpful there. Yeah. We'll see more of that anyway as we continue to look at what tests might be used for different series. So if I want to implement the ratio test in this case, take the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Usual, or by definition, or by the theorem, we have to have absolute values, and in this case, each of the terms are positive, so the absolute values aren't doing anything. I'll include them at first just for clarity of moving from here to here. So 3 to the n plus 1 divided by n plus 1 squared times 2 to the n plus 1 minus 1, they cancel, divided by 3 to the n divided by n squared times 2 to the n minus 1. Of course, division by a fraction is the same as multiplication by the reciprocal, so this is equal to the limit as n goes to infinity of, absolute values aren't doing anything, so I'm going to leave those off, 3 to the n plus 1 divided by n plus 1 squared times 2 to the n. So, and then multiply by the reciprocal here, n squared, 2 to the n minus 1, divided by 3 to the n. Again, a lot of simplification here, so n plus 1 factors of 3, n factors of 3, cancel, n factors of 2, 1 less factor of 2, cancel, and then polynomial divided by polynomial. So that will remain there, the polynomial that is. So this is the limit as n goes to infinity. Almost all of the 3's cancel, 1 remains, so 3 times n squared in our numerator, and the denominator, let's see, 3's are gone, still a remaining factor of 2, and then we have n plus 1 squared. So we have a degree 2 polynomial divided by a degree 2 polynomial. And we know that when we have such a scenario, that the limit is going to be the ratio of the leading coefficients, 3/2. 3/2, of course, is greater than 1. So this tells us that by the ratio test, the series of interest here, the sum from 1 to infinity of 3 to the n divided by n squared times 2 to the n minus 1. So this is larger than 1, and when the limit is larger than 1, we have divergence. So by the ratio test, this series diverges. And that's it. So in reality, right, the n squared here and the n squared did nothing. So the n squared that's contained in that did nothing, essentially, right? That's what we're kind of looking at there. So it follows along when we have a polynomial compared to something that's geometric. That polynomial isn't going to do anything. In fact, if we would have put the n squared up here, that would have just changed its location, right? N plus 1 squared would be up here, so n plus 1 squared would be in the numerator, and n squared would be in the numerator here, denominator here. So you would have n plus 1 squared in the numerator and n squared in the denominator, and it would also essentially have no effect on the outcome. It wouldn't have any effect, right? The geometric aspect here is far more powerful than the polynomial or rational aspect. So that's a little bit interesting that n squared played no role in the convergence or divergence of this series. So again, what does the geometric series do? The polynomial isn't going to do much of anything, and we can verify that through the use of the ratio test. All right, that's all that I wanted to share. Thank you for your time. I'll see you guys back in the workshop.